Hi there. This is the last part of Chapter 2, Lesson 3 in your physics workbook dealing with Newton's laws of motion. And today we're going to be reading pages 48 and 49 dealing with Newton's third law of motion. So let's start by taking a look at this. So it says, what is Newton's third law of motion? If you leaned against a wall and it didn't push back on you, you'd fall through. The force exerted by the wall is equal in strength and opposite in direction to the force you exert on the wall. Now, here's the key concept with Newton's law of motion. Newton's law of motion states that if one object exerts a force on another object, then that other object, the second object, exerts a force of equal strength in the opposite direction on the first object. So another way to state Newton's third law is that for every action, there's an equal but opposite reaction. Okay? So we always say that forces occur in pairs. Okay? So for every action force you will have a reaction force that is going to be the same size force, but acting in the opposite direction. Where it says action pairs. Pairs of action and reaction forces are all around you. When you walk, you push backward on the ground with your feet. Think of this as an action force. And in parentheses, it says it doesn't matter which force is called the action force and which is called the reaction force. Okay? The ground pushes forward on your feet with an equal and opposite force. This is the reaction force. You can only walk because the ground pushes you forward. It says in a similar way, the swimmer, figure 3, which is at the top of this page, I'll scroll up in just a second, moves forward by exerting an action force on the water with her hands. The water pushes her hands with an equal reaction force that propels her body forward. So it says moves because the water pushes forward when she pushes back on it. And if you take this part of the photo, see she's moving from left to right on the screen. Okay, so her action force, represented by the orange arrow, is going backwards because she's pushing the water backwards behind her as she moves her arm from front to back. But as she pushes, that is the water against her hand with the exact same size force, but in the opposite direction. And you can see that here is the reaction force, it's same size as the reaction force. So since the arrows are the same size, the force is the same size. Opposite directions. So that would be a really good example of an action-reaction pair. The only reason she will move through the water is because the water is pushing back on her, the exact same size force, but in the opposite direction. I'm going to scroll down to the question side margin. It says action and reaction force pairs are all around you, but they aren't always obvious. So they say write down a question about a situation in which you can't identify what force pairs are at work. So here's one example that you could consider, okay? What are the action-reaction forces when something falls down? Okay, if something's just falling down through the air, what are the action and reaction forces? Okay, it's not always going to be obvious. Okay, let's move on to motion. So it says if you drop your pen, gravity pulls the pen downward. According to Newton's third law, the pen pulls Earth upward with an equal and opposite reaction force. You see the pen fall, right? You don't see Earth accelerate toward the pen, though. So remember what Newton's second law said. If mass increases and force stays the same, acceleration decreases, okay? So the same force acts on both Earth and your pen. But since Earth has such a large mass, its acceleration is so incredibly small, you don't notice it, okay? Now, action reaction force cancel is the next. So it says, you have learned that two equal forces acting in opposite directions on an object cancel each other out and produce no change in motion. So why don't the action and reaction forces in Newton's third law of motion just cancel out as well? Well, action and reaction forces do not cancel out because they're acting on different objects. Okay? The swimmer that we three exerts a backward action force on the water. The water, though, exerts an equal but opposite forward reaction force on the swimmer's hands. So the action and reaction forces are acting on different objects. The hand force acts on the water, and the reaction force acts on the swimmer's hands. So since they're on different objects, they don't cancel each other out. Now, the last paragraph here, on the swimmer and the water, the volleyball here on the page, both exert a force on the same object, the volleyball. Now, each player, exerts a force on the ball equal in strength but opposite in direction. So in this case, the forces on the volleyball are balanced. Therefore, the ball does not move toward one player or the other. So the player right, and the player to the right of the net is exerting a force on the volleyball towards the left. Now, since they're exerting the same amount of force on the same object, the forces are equal in strength, opposite in direction on the same object. So in that case, they cancel each other out and the ball doesn't move. Okay? Now let's look at figure 4 with the box. It says all the horizontal forces on the ball cancel each other out. Okay, just as we're just taking. But in the dog illustration above, they ask us to use Newton's third law of motion to draw and label any missing force arrows for all of the objects. And so what we're seeing here, there are two force arrows beneath the dogs. Force arrow on the left shows its force pushing to the right on the box, okay? And then the force arrow beneath the dog on the right is pushing towards the left, showing the force the dog on the right is pushing against the box. Now, what forces are missing? What's missing are the two reaction forces. So if the dogs are pushing on the box, hey, the box has to be pushing against the dogs as well. So the two missing arrows would be an arrow pushing against the orange arrow on the bottom left, and then you would also have another arrow pushing against the arrow on the right, equal in strength, opposite in direction. Okay, so it's just missing the two reaction forces in this diagram. Let's take a quick look with rockets. It says Newton's third law of motion explains why rockets accelerate in space even though there is no water or air to push off of. Well, inside rockets, gas gets produced when the fuel gets burned. Okay, when the rockets push that gas backward out of the rocket, a reactive force occurs that pushes the rocket forward. So the true reason why a rocket can still move through space, even though there's no air or there's nothing out there, right, is because the exhaust gas that's pushed out of the rocket when the fuel is burned, that exhaust gas pushes back on the rocket with the exact same size force in the opposite direction, which still allows the rocket to move through space. Well, I hope this makes sense. Newton's third law of motion. If you have questions on this, please make sure to reach out and let us know. But this concludes Chapter 2, Lesson 3, Newton's three laws of motion.